class in 5 minutes. So, but we'll meet again in 2 weeks, and you'll get the data from us for the TGA and the vacuum or the volume calibrations we've done.
Okay, wonderful.
Wonderful. Yeah. Okay, thank you. And Ronnie, hope your stress goes down.
Yeah. Bye. Thanks.
What happened to Dr. Pimi? Why there's a stress?
Most probably some deadlines.
He looks there.
Okay. This is.
I've sent the meeting minutes.
Have you? Oh, fantastic. Can you keep track of the meeting minutes every time and just send it to everyone? That's better. This way everyone has them.
Yeah.
Good. And we're meeting again at 10, right?
Yeah.
High pressure test? Yeah. Okay. Wonderful.
So it started ringing a minute ago, so I clicked the video button and it stopped ringing, but it doesn't look like that answers. Also, I didn't know they would call so early.
They usually call pretty early.
Okay.
They usually call around like 52.
Well, I might have accidentally hung up after I answered it. I don't know. No call back.
I'm just gonna hang up on them.
It looks like it's on. Congrats.
So, good morning. Are these guys connected?
Yeah, I just don't think they have a camera.
Okay.
Ask them if they can hear us.
Hello. Okay. Everybody's tired. So, we finish what we discussed last time with respect to delta function. That is a very important tool that we need again and again and again. So let's have a final look at this. So we introduced the delta function as a derivative. Everything's good with you? How does it look? Hello?
We can see it.
Okay, thank you. So we introduced the delta function as a derivative of the step function, the Heaviside function. It is really important to fully understand that this is a kind of brief writing for limits. So the step function can be represented in a variety of ways by using any parameter like n or whatever. And then the delta function is defined as the limit of the derivatives of these smooth functions. Yeah. Also, there are many different ways to introduce the delta function. So actually, the meaning is simply that at any position, depending on the argument, the peak of the delta function goes to infinity. And you can define this in many different ways. It doesn't matter. For example, one possibility is to consider the normal distribution. So this is actually a pretty good way to always look at the delta function, that we have a certain normal distribution with a standard deviation sigma so centered at mu, the mean of this distribution, and in the limit that sigma goes to 0, then f of x will be given by the delta function. Again, there are many other ways. Actually, the biggest relevance of the delta function arises from probability theory.
One over square root of 2 by sigma squared.
Yeah. So actually, the delta function is the definition of an instantaneous probability density function, and every probability density function is represented as mean over delta functions. So the delta function is the fundamental tool to introduce probability theory. And we will also use it again and again. We will talk later about Green's functions, and you will see it even today. That's the reason why I talk about this. Yeah, as you can imagine, if the delta function is just a specific probability density function, so actually I always look at the delta function in this way, which is absolutely fine. Then it is also clear that it must have certain characteristic properties. As you probably know, any probability density function is defined to integrate to 1. That makes a PDF to a PDF. And accordingly, we have here certain properties. So the delta function integrates to 1. Actually, it is always highly beneficial to look at the relationship between the delta function and the theta function. So it is just the way it is, that usually a delta function appears below integrals. So, and then we have to solve these integrals. And as you can imagine, it will be highly beneficial then to represent the delta function as a derivative in order to solve such integrals. So there are other properties like this here. And another property is this here. So it turns out that in almost every case, one finds, so when we have to do real calculations, one finds the delta function to be multiplied with something, and then we take advantage of the basic property of a PDF that it is only non-zero at x is equal to a. So that means with respect to any domain x, we just have to account for the possibility of non-zero values of g of x at x is equal to a, because this is the only position where the delta function is non-zero. So this allows us to replace g of x by g of a, which is of course not affected by the integration. And then by taking advantage of the integration property of delta functions, we can conclude that this integral is equal to g at a. This is something that you should definitely know. We will use this again and again. That is, let's say, very important. That is the way to deal with integrals involving delta functions. By the way, most likely I will teach next semester probability theory, so this is stochastic modeling. So if you are interested to know more about it, there's, let's say, a possibility. And with respect to the last property, that is simply a reflection of the case that the delta function has the peak at x is equal to 0, and then it doesn't matter whether we go with delta of negative x or delta of x. That is also sometimes a thing that is important. So to have more excitement, we will also consider delta functions in 2 and 3 dimensions. And in this regard, it is just good to know about some basic sorts of writings. So when we write it like this, with an underbar here, the theta or the delta, then it means that the delta function is a function of any set of x coordinates, let's say running from 1 to n. Are they still with us?
I think so. One, ask them. So they can see if they're- I think
Hello?
the cameras are just turning off. Seems like they're connected. That little one down in the corner says there's one. site.
Can you see what we are doing here?
You have to respond with your mics because we can't see you. So can you let us know, like with your mics, that you can still see us?
Looks like there's some connection problem. Last time not last time, but a few last times. When you were in Japan. Oh. Can I ask you something?
Sure.
Shifting property or a shifting property?
Actually, according to my knowledge, you can use both. I always follow the textbook. Hey, can you hear us? Yes?
Either one. Yeah, we got the one's commutative.
How does it look for you?
It's good now. We can
That makes sense.
Okay.
Too.
So I follow here textbook notation, but usually I talk about the shifting property, which makes perfect sense from my viewpoint. So regarding this writing, we will use this today. Yeah, that is not too far. We have here any vector of x, and so technically, let's say the delta function in 3D depends on x1, x2, and x3. Yeah, so it can be anything. It turns out that we have here the product of single delta functions.
It looks like the separation of variables.
Yeah. And obviously the reason is the basic property of the PDF that it has only peaks at x1 is 0, x2 is 0, and x3 is 0, and that makes this separation possible. Yeah, but let's say the writing on the left-hand side is simply a brief writing for the right-hand side. Okay. How do you feel about PDFs? Do you like it?
It's better than PDEs.
So what makes this little uncertainty?
You need to see it more. You need to see more.
Okay, very reasonable. So that was, let's say, a technical thing that we should consider, and then we go back to our initial value problem. And this is real, so you will see things like this in homework and also in tests, but not on Monday. So what we actually would like to do is to look at the wave equation in 3D, subject to several initial conditions for the position and so the displacement and its velocity. So at the end of the day, we will combine this PDE with certain conditions on u at t is equal to 0 and ut at t is equal to 0. As you will find out very soon, that is actually not absolutely trivial. So we talk here about 3D problems, PDEs, so it is kind of interesting. And what we will do is to approach this step by step. So we will talk about certain pieces. So let's say extensions of the solution, so let's say ways to set up the solution procedure, and at the end we bring everything together and you will see the complete solution. But I think you will appreciate it to go through this step by step. Otherwise it is kind of very challenging. So we focus here on radially symmetric solutions. So we work here with spherical coordinates. So we have the radius and two angles, and we don't care about the two angles. So we say that they do not come into play here. And as you will see, that is still a pretty good problem. So under this condition, that we have radially symmetric solutions, we can rewrite the Laplace operator in terms of the right-hand side. So it is then given by, so when we multiply it with u, then, sorry, with r, and here is a missing r. So just see. Then we get the right-hand side here. And based on this, we concluded last time that r times u is given by these two contributions f and g at r plus ct and r minus ct. R is defined as square root of x1 squared plus x2 squared plus x3 squared. So the question is what to do with it. And what we will do now is to look at a first version of the initial value problem given by the following. So let's say number 3 of this procedure was data functions. Step 4 is now initial value problem version 1. And again, we will expand the setup of the problem in the following. So we work here in 3D, and actually our goal is to deal with a problem for setting u at x at t is equal to 0 equal to some f, and ut at t is equal to 0 to any function g. And then we would like to get the solution to this problem depending on the input f and g. So a simplified version of this case is that we look first at a delta function input, and this is exactly what I showed you before. So this delta function is delta of x1 times delta function of x2 and delta function of x3. So we have here a certain forcing of this PDE given by the delta function. And the question is how the PDE responds to this delta function. This is actually not any little academic exercise, but it is a fundamental way of solving PDEs to look first at the response of the PDE to delta functions and to expand this then to get the solution of the PDE for any functions. This is closely related to the idea of Green's function, as you will see a little later. So for this sort of calculation, you can certainly do this in a kind of abstract way by working with these writings, by having always the understanding that we talk here about the limits. I follow here the textbook and use this writing for the delta function. So we introduce here a certain epsilon, and actually what this means here is that we look at a three-dimensional normal distribution, which is actually isotropic. So there are no correlations between the three components. So this probability density function is simply given by the product of single probability density functions. And the epsilon plays a role of a squared standard deviation, so the variance. And so this is, consider a normal distribution in 3D. And consider that the standard deviation goes to 0. And this is our representation of the delta function. Again, it would be possible to use several other writings. All these setups are equivalent. There is no difference, because when we take the limit, we always talk about the same. Yeah?
Would be magnitude of vector x?
Yeah.
And then the epsilon in between would be squared? Yeah. Epsilon is?
The epsilon in where?
Like e to the minus magnitude of x squared would, over the 4 epsilon.
Yeah. So this is actually, so the x squared is x1 squared plus x2 squared plus x3 squared. Yeah? And the epsilon, again, is the variance, which goes to 0. So this is one possible way, and the only advantage of this is that it allows us to do explicit calculations when it comes to dealing with this problem. And at the end, we will go back to an delta function. I asked you to note that this is a three-dimensional PDF. But you can see this by the 1 over something to the 1.5. So in each dimension, there is the specific weight of the PDF square root of the effector times the standard deviation. Yeah. And here the 1.5 reflects a three-dimensional probability density function. That matters, as you will see later. So the input is isotropic. It depends only on R, and that simply means that the data are radially symmetric. Therefore, we can proceed with our solution procedure to talk about radially symmetric solutions. Okay, so the data to the problem symmetric. Therefore, solution has to be expected to be symmetric. So this means we can work with our conclusion obtained before. Which is pretty good. So it looks like we have already an expression for the solution. So from a technical viewpoint, what is still left to do here? Yeah, at this point the f and g are unknown functions. We only know that they depend on these two arguments. And what should be the specific goal of our next step? Yeah. So what we would need to do is to relate the input for u at 0 and ut at 0 to f and g. So we have two conditions to find two functions. So the point is that the two conditions for u at t and ut at t do not depend on t, but f and g do. Is this kind of disturbing? Then otherwise, is it a good idea to begin at all with this calculation? So let's make it slightly more specific. The initial conditions are functions of R, right, and not of T. And what we would like to get are functions of R plus Ct and R minus Ct.
We just simply change the argument of those functions?
Exactly. Excellent. Yeah. So what we will do is to find f and g as functions of R. And due to the fact that these functions depend only on one argument, we just have to use these expressions later by replacing R by R plus Ct and R minus Ct. So this is something that one should know about the solution procedure. And again, at some point you will definitely have the chance to use this. So that this sort of problem is actually a good problem even for the final, because it is something where one has to demonstrate some understanding and knowledge. Otherwise, technically, it is not horrible. So what we will do is to use the initial conditions to conclude so this gives us f equals negative g, and So obviously, this is the condition at t is equal to 0. And this is the condition obtained by using the structure of u t at t is equal to 0. So what we do here is to differentiate this function first by t, which produces the positive c, and of course the r is unaffected. And here, due to the inner derivative, we get a negative c over r. And this needs to be equal to the delta function of r. So what we can do here is to conclude that g prime is this here. Again, when I use primes, it is always done with the understanding that we consider the derivative by the only argument of this function. So what is a good next step?
Find f prime and integrate both f prime and
Excellent.
f prime.
So actually you can do it in several ways. At the end of the day, we simply want the f and g, right? So what we can do here is we have already an explicit expression for g prime. And what we do next is to consider g by using the limit formula for our delta function. How does integral look like? Something to say, oh my God.
It's roughly an expected value, isn't it?
Oops, we would like to solve it in the simplest possible way. Yeah?
Yeah, but the integral, that's going to be roughly an expected value?
Yeah, you can look at this in this way. Yeah, it is that is correct.
Yeah.
But the question is still.
You can do substitution of variables that are in front of the x.
Yeah, actually there are several ways to solve the integral. You also. Yeah, so let's say that would be, here we work with the explicit representation of the PDF. Actually, whenever you have exponential functions and something next to these functions, it is good to ask whether you can relate this factor to the derivative of the exponential function. And a second look here shows that this is very much the derivative of the exponential function. So what you can do here is to do one intermediate calculation like this here. And on this basis, you can see that you can relate the two terms here to the derivative of this exponential functions. You just have to multiply the term here with epsilon over c. And on this basis, it is not difficult to conclude about the following. And at this point we use f is negative g. And by putting all of this together, we conclude obviously the C is balanced by the negative C of the F, so there is no contribution due to the C. And what we can do next is to write it like this. Just for full clarity, obviously what we did here was to replace f and g as functions of R by the arguments that we need, R plus Ct and R minus Ct. So what about this result? Do we like it? What does it tell us? Actually, where are the peaks of these delta functions? Plus and minus what? Yeah, except that C and T are considered to be positive. So data functions have their peak at a zero argument, right? So the point with the first data function, we are just fine. There is a peak at R is equal to Ct. Yeah? R is defined as square root x1 squared plus x2 squared plus x3 squared. C is physics-wise a positive constant, it's a velocity, and T is physics-wise positive time. Exactly, yeah, exactly. So there's no need to account for this because the argument is always positive. And what we get out of this is actually this here. And this is called the fundamental solution to the wave equation in 3D. So the way of addressing the problem is a typical setup. So we look at data input to initial data, so to the PDE considered, and we ask how does PDE respond to such data peaks, and this is our result. And at this point, we can move on. I can get rid of it, yeah? So this is about the initial value problem version 2. And this is now an extension of the case that we considered before. So before we talked about a data function velocity, and here we talk about any function g. And what we can do at this point is to relate the g to data functions. Which is correct according to the shifting property of the data function and the normalization property of data function. So this is just another way to present the g of x. And I will write the following in order to make it fully clear. This actually is still data function input multiplied with certain numbers, g dy, which is actually the probability to find g values, but at the end of the day, from a technical viewpoint, it is just a number. So we still have an data function input, and when we slightly expand the approach that we used before, then we can conclude that u of x and t, which is the solution to this problem, is given by this stuff here. Bless you. So if the input is a sum over this amount of data functions multiplied with numbers, then the solution is also the sum over all these fundamental contributions. So in other words, we got here a rather simple expression for the solution. And what we can do, certainly, is to take advantage of the fact that the data peak is at R is equal to CT. So, and then we can write the solution like this. This is one valid representation of the solution, and usually it is the best way to represent the solution. But what one also can do is to take again advantage of the fact that the delta peak is at R is equal to CT, and then we can write the solution like this. So these two writings are equivalent. You can do it in one or the other way. When it comes to concrete calculations, it is usually the best to work with the delta function because it provides such a simple understanding. But again, for some problems, it may be beneficial, and of course, depending on the structure of G, to work with a formula below that. So this was one further step towards the complete solution to the eigenvalue problem. Next time, we will continue with looking at non-zero input for u at t is equal to 0. And after that, we will soon have the complete solution to the initial value problem. Yeah?
What is the symbol?
This is SCT. Yeah?
The signal? Okay.
Yeah? CT. Yeah? So this is a sphere with center x and radius CT. So have a wonderful weekend. See you on Monday for the test. Here. Yeah.